Let's work an application problem. We want to find the magnitude of the equilibrant of forces of 48 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. Then find the angle between the equilibrant and the 48 newton force. So what we've got, and we're going to draw a picture, we've got a 48 newton force and a 60 newton force acting on a point A. The angle between those two forces is 50 degrees. We want to, first of all, find the magnitude of that equilibrant force. After that, we're going to find the angle between it and the 48 newton force. So here's a picture that represents what we know. Here's the point A right here. I've got a 48 newton force, a 60 newton force with a 50-degree angle between them. I've drawn some dashed lines to form a parallelogram. So this line is parallel to 48, which means its length is also 48. This line is parallel to that line, so it also can be considered having magnitude 60. Because this is a parallelogram, this 50-degree angle and one adjacent to it are supplementary, which means this is 130 degrees. 130 plus 50 is 180. What that allows me to do is consider this triangle above what I've drawn as a horizontal line. And in that triangle, I want to find the magnitude of AC. AC represents the resultant vector, or the equilibrant vector, of the 48 and 60 newton forces. So I want the magnitude of AC. According to the law of cosines, that magnitude squared in just this triangle, in this top triangle, is equal to 48 squared plus 60 squared minus 2 times 48 times 60 times the cosine of 130 degrees, which is the angle between those two vectors. Now, if you crunch this number on your calculator, you'll see that the magnitude of AC squared is about 9,606.5, approximately, not exactly. And so the magnitude of AC's, the square root of that is 98. So the magnitude of that equilibrant is 98 newtons, and that's part of what I was looking for. Well, let's sketch that equilibrant vector on our picture. The equilibrant vector would have its initial point at A and point to the left and have a magnitude of 98 newtons. It's a good idea to sketch that now because we are also charged with finding the angle that that vector makes with the 48 newton force. So we're looking for this angle. What we can do is find the angle in the triangle and subtract it from 180 to find the angle we desire. To find the angle in the triangle, which is angle A, or labeled angle A, I'm going to use the law of sines, angle B, which is 130, and the 98 newtons, as well as the side 60. So let's put together a law of sines statement. Sine of angle A over side A equals sine of angle B over side B, and fill in what we know. We're looking for angle A. We know side A is 60. We know angle B is 130 degrees, and we know side B is 98. We just found that. I'll multiply by 60. Sine angle A is 60 sine 130 degrees divided by 98. And I'll solve for angle A by doing the inverse sine of this. Angle A in the triangle comes out to about 28 degrees. So the angle that our vector, our equilibrant vector, makes with the 48 newton force is found by taking 180 degrees and subtracting 28 degrees, which comes out to 152 degrees. And that's the angle we were looking for. Let's work an application problem. We want to find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal, assuming there is no friction. So we've got a ramp that forms an angle of 20 degrees with the horizontal and a 50-pound wagon. So I've drawn some information on a sheet. This is supposed to represent the ramp. It forms an angle of 20 degrees with the horizontal. The wagon is here on the ramp. Its weight is 50, which is indicated in the picture perpendicular to the horizontal or perpendicular to the ground. What I've done is taken that 50-pound weight and broken it into two components, perpendicular and parallel to the ramp. This angle in the right triangle I've drawn matches the angle that the inclined plane makes with the horizontal in that it is 20 degrees. What I'm interested in finding is the magnitude of this side of the triangle with an angle of 20 and a hypotenuse of 50. So to find that, I can use, since for this angle the side I'm looking for is opposite, let's call it x. To find x, I can say that the sine of 20 degrees is the opposite side over the hypotenuse. I can multiply by 50, and all I need to do is crunch this number on a calculator to get x. X comes out to approximately 17. The units on x would be pounds. It takes a force of 17 pounds to keep the wagon from sliding down the inclined plane. Let's work an application problem. A force of 16 pounds is required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? Well, I've drawn a picture, and here's the incline. This is the angle theta that I'm interested in finding. What I've done is assumed that the lawnmower is roughly here and shown that its weight, its 40-pound weight, is perpendicular to the horizontal. Weight pulls straight down. And I've broken the weight into two components, one perpendicular to the incline and one parallel to the incline. The component parallel to the incline is the 16-pound force that's holding the lawnmower on the incline. What I want to find is the angle the incline makes with the horizontal, which matches exactly this angle, I'll call it theta, in the triangle that I've drawn. That angle theta is opposite 16, and I also know the hypotenuse. So I can use the sine function and say that the sine of the angle that I'm looking for is the opposite side over the hypotenuse. And with the help of a calculator, find theta by finding the inverse sine of 16 over 40. That angle comes out to approximately 23.5784 degrees. Let's work an application problem. A ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from port, and what is its bearing from port? Well, we need to draw a picture to represent this problem, and feel free to refer back to the description of the problem at any point. What we know is here, P for port. The ship leaves port at a bearing of 28 degrees and travels 8.2 miles. At that point, the ship turns due east and travels 4.3 miles. Well, in here, we've got 118 degrees. The way that you get the 118 degrees is to realize that if you were to draw horizontal from P, the angle in here could be found by taking 90 minus 28, which is 62, and that angle would be exactly equal to this angle, which is 62, and that plus 118 would be 180, which is where the 118 comes from. In any case, or with all that in mind, or in addition to that, what I'm interested in finding is, given all this information, what is the length of PE, or how far is the ship's here at E, from port, which is P. So if I want the length of PE in this triangle, I'm going to use the law of cosines. The length of PE squared is equal to 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 times the cosine of 118 degrees. Now I need to calculate that value. The length of PE squared then is about, if you do this on your calculator, 118.84. Using a square root, or finding the square root, the length of PE, which is the distance of the ship from port, is about 10.9 miles, and that's part of the answer that we're looking for. What we need to do now is find angle APE. Once we find it, we add it to 28, and we have the bearing of the ship, remember the ship's here, from port. To find the bearing, or the angle in the triangle, I'm going to use the law of sines. Angle APE is opposite side 4.3. I have 118 degrees opposite the side I just found. And let's put together the law of sines. What we're going to do, or what we're looking for, I should say, is angle APE. The sine of that over side 4.3 is equal to the sine of 118 degrees over the side we just found, to be 10.9. I'm going to multiply by 4.3, so the sine of APE is 4.3 sine 118 degrees divided by 10.9. Then with the help of a calculator, I can get APE by doing the inverse sine of this in degree mode. APE is approximately 20.4 degrees. But that's not the answer that we're looking for. We take that, add it to the original 28-degree bearing to get an angle of 48.4. The bearing of the ship from port is 48.4 degrees.
An airplane that is following a bearing of 239 degrees at an airspeed of 425 miles per hour encounters a wind blowing at 36.0 miles per hour from a direction of 115 degrees. Find the resulting bearing and ground speed of the plane. Well, of course, an accurate sketch is essential here, and there's lots of information. So here it is. Let's begin over here where I'm saying the plane is taking off. And what I'm saying is vector C, which is in blue, represents the airspeed and bearing of the plane, the bearing of 239 degrees and the airspeed of 425 miles per hour. Next, vector A, which is in red, represents the speed and direction of the wind. That direction is 115 degrees, and that's written here. And what we're interested in eventually is finding angle ABC, which is the angle inside of here. And once we've done that, we can use law of cosines. So to get there, let's go back to the plane, which is on a bearing of 239 degrees here, and say that if we were to subtract 180 degrees from the 239, it gives us the angle inside here, which is the angle SAB, and that would be 59 degrees. The reason that's of interest to us is, notice that we have two north-south lines, which means they are parallel, being cut by this vector C, so that's the transversal, and therefore alternating interior angles are equal. And more specifically, what that means is angle AB n sub 1 is going to be equal to 59 degrees. Now, let's go to the wind speed. For the wind speed, we had the angle of 115 degrees. And so if we subtract the 90 degrees, we see that that would give us an angle of 25 degrees here. Now, of course, what we're interested in is the angle inside here, and we'll find that by noticing that angle W sub 1 BC, so this angle here, is a vertical angle with this angle E sub 1 BF. Vertical angles are equal, which means this angle W sub 1 BC is equal to 25. The reason that's helpful is the angle inside here, which we can say is N sub 1 BC, is complementary with this angle of 25 degrees, and therefore this angle is 90 minus 25 degrees, so it's 65 degrees. So that means angle ABC is the sum of those two angles. So I will write angle ABC is equal to 59 degrees plus 65 degrees. That's equal to 124 degrees. So now we're going to use the law of cosines to help us find the length of B. So let's use the law of cosines. Here I've written it, and so now we're going to substitute in the information that we're given. So of course we're trying to find the length of B, so that remains the same, and that's equal to the quantity of A, which is 36. That's for the speed of the wind, and that we have to square, plus C, the vector C, which is 425, and again we have to square that, minus 2 times the absolute value of A, which of course is the 36.0, times the absolute value of C, the 425, then times the cosine of the angle ABC, which is 124 degrees. Evaluating that on a calculator, we find that the absolute value of B squared actually is going to be approximately equal to 199,032. And then, because we're interested in a length here, we're interested in only the positive square root, so the absolute value of B is going to be approximately the square root of 199,032, which when we substitute and evaluate on the calculator will give us 446. Well, now that we have the length of B, we can use the law of sines to help us find angle that alpha is the way we called it. And so we write the law of sines, which is going to be the sine of angle alpha divided by the side opposite, which was vector A, 36.0. And that's equal to the sine of 124 degrees, which is angle ABC, divided by the side opposite it, which is side B, 446. So now we want to find alpha, so we multiply both sides by the 36, and we have sine of alpha is equal to 36.0 times the sine of 124 degrees divided by 446. Again, evaluating this on the calculator and using the inverse sine function, we can say that alpha equals the sine inverse of this expression, 36 times the sine of 124 divided by 446, and that is approximately equal to 4 degrees. So we need to add that 4 degrees to the original bearing of 239 degrees. And so 239 degrees plus the 4 degrees gives us a bearing of 243 degrees. And that's the bearing of the plane when it's been obviously adjusted by the wind. So let's take a look at the illustration to get a sense of what we're talking about. This angle alpha is the effect that the wind blowing from this direction has on the bearing of the plane. And so that angle alpha we just found was 4 degrees, which means we added it to the 239 to get this entire bearing, which we said was 243 degrees. And so the flight of the plane relative to the ground is actually this vector b, which therefore has been adjusted for the fact that the wind would blow the plane in this direction.